Thanks. Hey everyone, my name is Yondon. As Dan mentioned, I'm working on a project called Livepeer, which is a decentralized video streaming protocol. And I'm going to talk a little bit today about trying to secure micropayment protocols and just brief overview of what I'll be discussing. I'm going to start off by trying to give a very brief tour of micropayment systems in the past and the present, the motivation behind them. Then I'm going to talk a little bit about two different types of protocols that have seen some amount of attention, especially in the Bitcoin and Ethereum space. The first one being payment channels, and the second one being probabilistic micropayments, which actually have a longer history in the field of cryptography research. I'm going to present payment channels very briefly because I feel like there is a fairly wide amount of literature and knowledge about it being posted on the web already. So for the sake of a 20-minute presentation, I won't focus too much on it, but I'll just present it as primarily to serve as a point of comparison as I talk a little bit about the security model for probabilistic micropayments in the context of Ethereum. Then I'm going to try to go over some common client security considerations that I think are common to both types of protocols and generally for off-chain protocols that end up requiring certain on-chain interactions generally. And then lastly, I'll touch upon some of what I think are interesting topics in the probabilistic micropayment security model that are necessary in order to actually secure against loss of funds. So to start off with, why care about micropayments at all? I think some interesting and potentially compelling use cases include pay-as-you-go digital service business models that might range from outsourced computation, have certain computation be metered, or other types of content consumption, such as streamed video or audio. Related to that, we have machine-to-machine recurring payments, and spam prevention might be interesting as well. In terms of efforts in the past, there's actually been a lot of efforts at micropayment systems in the past, even pre-blockchain and cryptocurrency era. We had efforts such as like Millicent and NetBill, and at one point, the W3C even proposed introducing the concept of a payment request information in the HTTP error code, although that ended up never getting pushed through. And then in the field of cryptography, this has actually been a pretty interesting topic for a lot of researchers. We had Ron Rivest and Adi Shamir working on payword and credit. And we also had Wheeler and Rivest working on the first iterations of a probability-based lottery ticket approach to micropayments. That being said, there seems like there's been a lot of efforts in the space of micropayment systems, but that begs a question: why have none of these things ever seen deployment or use in a live setting? I think two potential reasons include the high deployment costs and transaction costs involved with relying on centralized payment processors and banks. The second one, I think, has to do with oftentimes mental transaction costs are greater than the actual computational or economic cost involved with a micropayment. Nick Szabo writes an interesting essay about this that I encourage people to check out. But related to this, perhaps it's the case that human-based decision-making when it comes to micropayments may not be as feasible in certain use cases, but something that might be more practical is if you had automated agents that send these micropayments on behalf of users for certain types of digital services. So what do we have in the present with the advent of Bitcoin and other cryptocurrencies and blockchain-based systems? We can actually rely on smart contracts deployed on blockchains as a trusted, transparent third party to actually process these payments. That being said, micropayment systems that rely on every single transaction being confirmed on chain are impractical due to long delays in terms of service due to blockchain confirmation times, and in addition to that, just high transaction costs that might end up exceeding the value being transferred, which is likely the case when we're talking about micropayment. But not all hope is lost. We can still try to construct protocols that rely on the blockchain for certain types of interactions, but push a lot of the logic off-chain, so we can have clients communicate directly with each other off-chain following a particular protocol, and they only have to go on-chain for things such as settlement or dispute resolution. So touching upon payment channels briefly, the general idea of payment channels revolves around clients or peers sending each other signed state updates. And prior to this, they would have deposited on-chain funds that they're using for these transactions. And when they send these signed state updates back and forth, all it does is it redistributes the funds within that channel. and you can be sending micropayments in one direction and micropayments in another direction. But at the end of the day, when you want to settle, that's the only time that you have to incur on-chain transaction fees. These channels can be connected together to form a payment channel network. And there's mainly two types of topologies. You can have a routed multi-hop network that might be more decentralized, or you might have a more centralized topology that involves a hub and spoke model, where instead of trying to find a path within a decentralized network for nodes to relay your micropayment transactions, you have a single hub sitting in the middle where everyone opens channels with the same exact party, and that party relays all transactions for you. So it has a cost in that it is more centralized, but at the same time, it has a better user experience because you don't have to deal with things such as pathfinding. In the normal case with payment channels, you have one deposit per counterparty. So that can be kind of onerous if you need to work with multiple counterparties and you need to incur on-chain transaction fees for each individual deposit. It gets a little better with payment channel networks because if you have the ability for relay nodes or hubs to relay transactions on your behalf, then you don't necessarily need one deposit per counterparty. You can have a single deposit and then just interact with the rest of the network by having the network relay your transactions. But this doesn't come for free. You have additional actors that you need to think about, additional incentives you need to think about, and you also need to make sure that none of this infrastructure fails, because you have to think about instances where what if the hub fails, what if the hub goes offline, what if any of these relay nodes go offline. So these aren't intractable problems, but I think are just things worth considering when thinking about what type of protocol to use. So that brings me to the next topic, which I think is worth exploring because it might not necessarily fit all use cases, but perhaps it fits certain application use cases, and that's probabilistic micropayments. And the general idea behind this protocol is that rather than me sending you an exact micropayment, I send you a lottery ticket where the lottery ticket has some face value that will pay out if the ticket actually wins. And there's some winning probability that's pre-negotiated for that ticket between two particular parties. And the micropayment itself is essentially the expected value of that ticket. So if you have a $100 ticket and only 10% chance of winning, then the expected value is $1. So this isn't that meaningful if I just send you like one or two of these tickets because the law of large numbers never has a chance to take place. But if I know that I'm dealing with a high volume application use case where a lot of these micropayments are going to flow through and all these micropayments are being paid for a granular service, then this might be acceptable because over the course of many of these tickets, the probability will play out such that I know that I'm being paid on average. So obviously this doesn't work for all micropayment use cases, especially if you're expecting to have these one-off interactions. But if you expect to have continued relationships with people such that you're paying large volumes of micropayments, then it might be acceptable. And the benefit here is that you can have one deposit for many counterparties, and this comes without the requirement for additional actors to consider and their associated infrastructure and what happens if it's online or offline. And as I mentioned before, it helps with many large volume micropayments. As I mentioned at the beginning of the talk, there's actually a fair amount of history in this space stemming from work from Rivest, Wheeler, etc. There was work on a Bitcoin implementation by researchers from Cornell, and there was actually also an interesting proposed work that integrated the zero cash protocol with probabilistic micropayments to basically achieve this type of payment protocol with anonymity. And finally, there's been some interest in the Ethereum space from projects such as Orchid, which is working on decentralized VPN, in addition to Livepeer, which is the project that I'm currently working on, and we're currently exploring this particular work. So this is a diagram of generally what the flow would look like, where if we have Alice, Bob, and Charlie, Alice might be sending multiple tickets to both of them simultaneously, and perhaps none of them win except a single one sent to Charlie. If the single one sent to Charlie wins, it has the opportunity to settle on chain with that ticket. And each party knows that they're being paid on average a fair amount. And if they're being paid many of these micropayments over time, then they know they'll be compensated fairly. And the only time that they actually have to go on chain is if one of these tickets pays out. So it's worth asking, like, why even think about this when we have payment channels? And I think some of the properties that I think are nice are one deposit per multiple counterparties, many large volume micropayments, and then also the flexibility of ticket parameterization. You can always modify the parameterization of the ticket in terms of its face value and winning probability, and that can help you adjust to what the gas price fluctuations on the Ethereum blockchain are right now. So if you have massive gas price fluctuations upwards and it becomes more expensive for transactions to go through, you're always able to parameterize your tickets such that it's always going to be worth it for you to settle that ticket on chain as long as you apply some margin on top of that transaction cost. And relative to payment channels, you can achieve some of these things with payment channels as well. But as I mentioned, they also require a lot more reasoning in terms of the infrastructure that's required. And I think there's a lot of great work that's being done by teams in the Ethereum space and other cryptocurrency projects to build some of these networks, such as applications have access to them right out of the box. But I think it's still at a relatively early stage, and I think it's worthwhile seeing if some other protocol can be used for certain application use cases, not all use cases, such that it fits this particular setting, but not all other settings. So probabilistic micropayments might be good for high volume use cases. They might not be as good for low volume use cases. And in addition to that, if the probabilistic nature of the lottery tickets is unacceptable for UX. So if we're talking about automated agents running on machines that users don't necessarily need to monitor every single second, then I think there's an opportunity to create a nicer UX such that some of the probability-based nature of this scheme can be hidden. But if it's the case that the balances need to be monitored every second, I think it's a little harder to create a more compelling user experience, which might be a non-starter for certain use cases. So before I get to the security model of probabilistic micropayments, I think it's worth highlighting some common client security considerations. So all these types of off-chain protocols, their security properties always make the assumption that you have a live blockchain such that you can always eventually confirm your transaction on it. And also there's an inherent like non-censorship assumption as well. If you have miners censoring your transactions, it's game over, like all of these security properties go away. So you kind of have to assume that right out of the box. In addition to that, there's two things I think that are worth highlighting. So clients generally, these are always online computers, and they need access to a signing key usually because they need to sign messages back and forth with another client. And often what this means is that you need to have your signing key hot on an always online computer, and that presents an attack vector. And if you lose that signing key, that could be devastating to you. And in addition to that, clients need to always perform automated actions on behalf of the user. And in certain cases, there's a time bound on when these transactions need to be included. So it needs to be the case that the client needs to be robust enough such that no matter what's happening on the blockchain, whether it's congested or not, if there's a scenario where you need to get a transaction in, it needs to know how to get that transaction in a timely manner before some timeout period. So timely transaction confirmation. In a lot of cases, like let's take payment channels, for example, there's usually a dispute resolution period where someone might go on chain and there's a timeout period where someone else can respond saying, hey, this is an invalid state update. This is from an older point in time. You shouldn't be able to do this, and this is cheating me out of my money. So your client can automatically do that for you, but what happens if the gas price fluctuates? What happens if it submits the initial transaction such that it has a sufficient gas price and gas prices shoot up such that the confirmation time increases because you didn't attach a sufficient gas price to it, and then you exceed the timeout period. So generally clients need to be robust against this, and they need to know how to bump up the gas price and make sure to replace transactions correctly. But it's also worth taking into account the possibility that what if your client needs to submit additional transactions in addition to this dispute resolution transaction? You need to make sure that the client is able to handle the account nonces for these transactions correctly and make sure none of these transactions get stuck in limbo. The next one's key security. So the most, I think, ideal user experience would be I can just create an on-chain deposit that's really big, and I can avoid additional transactions for topping off that deposit. But this also comes with a fair amount of risk, especially if your deposit and withdrawal key is the same as your signing key, because this means the key that has authority to withdraw your funds. So if you deposit a large amount, it has the ability to withdraw that. If that's the same as your signing key, then this means since your signing key needs to be hot on an always online computer, then the key that's authorized to withdraw your large amount of funds is also sitting on an always online computer. So I think it's usually worth asking, does the off-chain protocol that you're using support the ability to have separation of concerns with keys? So obviously you can do a lot to work on key management offline, but generally does the protocol support the ability for usage of multiple keys such that you don't need to have your deposit withdrawal key be the same as your signing key? Cool. So that's some, I think, worthwhile common client security considerations. And then moving on to the security model for probabilistic micropayments. If anyone's interested in the security model for payment channels, we can talk about that later, but there's also a lot of material on that online. So for probabilistic micropayments, the first thing that's worth talking about is double spends. So when we're working in this offline environment where I'm expecting a response from someone and they're going to respond to me prior to seeing any confirmation on chain, you always run the risk of encountering double spends. So how do we tackle this problem? One potential solution is to have any sender also have a non-spendable penalty escrow in parallel with the deposit. Deposit is used to fund the lottery ticket payments. The non-spendable penalty escrow is there to ensure good behavior. And in order to make sure that the penalty escrow doesn't disappear, you can implement a delayed withdrawal mechanism saying that, oh, if you want to withdraw your penalty escrow, you need to wait some period of time T, and everyone can see that you initiated withdrawal. So if they have any outstanding payments that they need to be cashed in, they can do so during that time. But this is still vulnerable to the fact that if I have a particular deposit and I am trying to send someone a lottery ticket, I can create a separate account. I can create a ticket that always wins because I am my own counterparty in this transaction, and I can send that ticket to another account that I own, and then I instantly drain my deposit. So my deposited funds could still disappear. So how do we deal with this? We need to make sure that the penalty escrow is actually sufficient to deter this type of behavior. So this begs the question, what is an adequate penalty escrow value? So the penalty escrow value basically needs to be greater than the additional utility that you can possibly gain from double spending within the period of time prior to you being detected. So there's some interesting work on, I mentioned earlier, this paper, Decentralized Anonymous Micropayments, that combine the zero cash protocol with probabilistic micropayments. But in addition to the work on anonymity, they provided an interesting economic analysis in that paper for this double spend scenario that I encourage people to check out. I think it's pretty interesting, but generally they propose ways to bound the maximum amount of financial activity that a particular sender can take part in during a period of time until double spend detection. And this generally involves trying to bound the receiver set so you know exactly how many double spends that can happen simultaneously, in addition to having clients define a maximum payment rate that they're willing to accept during a period of time to help balance that risk. And then based upon that, you can try to derive an adequate penalty escrow value that is enforced and that senders need to have, and they stand to lose if they're caught double spending. So what does it look if you double spend? So similar to the previous diagram, we have Alice, Bob, and Charlie, except this time Alice does not have a sufficient deposit to pay both Alice and Charlie, to pay Bob and Charlie, because 2 lottery tickets paid out. And what would happen is that the first lottery ticket gets cashed in and there's a sufficient amount, and now there's an insufficient amount for the other lottery ticket. So this constitutes a double spend because the same amount of money is used twice for 2 different types of tickets. And the second lottery ticket, if it gets cashed in, then we decrease the penalty escrow of Alice to 0 and they get slashed. The second thing that's worth talking about is how do we actually generate random numbers for this type of protocol? I think it's worth mentioning that there's 2 different methods for actually determining whether a ticket wins or not. You can rely on an external indicator or an internal indicator. So an example of an external indicator is we can say that we have some random beacon somewhere that neither party can predict the output at some given point in time in the future. And we just agree at this given point in time in the future, we're going to get a value from the random beacon, and we're going to use that to determine whether a ticket won or not. So an example of that would be, we can say that we'll use the block hash 10 blocks from now, and neither party should be able to predict that. And once 10 blocks have elapsed, you can check that block hash and use that to determine whether a ticket won or not. But this has some downsides as well, not only due to the fact that you have to wait that period of time until that value becomes available, but also in a proof of work network, obviously miners are able to control the block hash value somewhat, and it's really only the scenario that they would do that is if the value for manipulating the block hash is actually greater than, well, the value for manipulating the block hash is greater than the value that they stand to lose from lost time trying to grind through many blocks. So if it's ever the case that the value of the lottery ticket being cashed in exceeded the amount of block reward, then that could be problematic. So that might not be the case all the time, but I think it's worth highlighting. We're just going to talk about internal indicators, where internal indicators are determined by the parties interacting. So how do we do this? We can use an interactive protocol. We can use a commit and reveal process, which generally entails the recipient first generating a random number. Let's call it recipient rand. And then it's going to generate the commitment for that just by hashing that random number. That gets sent to the sender as a part of an initial handshake process. And then what the sender does is every subsequent ticket that it generates, it includes this commitment. And in addition to that, it also includes its own randomly generated sender nonce. On the recipient's end, when it receives this ticket, it can check if it won. And if it won, then what it's going to do is it's going to open its commitment by revealing its original random number. And this needs to match up with the commitment included in the ticket. And then afterwards, it's going to hash the original random number value that it generated with the sender nonce. And if this value is less than the winning probability, then the ticket wins. And I can submit this to a smart contract that knows how to do the proper validation. And if the validation steps pass, then it'll pay out to the particular submitter. So this is a diagram showing the general flow. We have Alice and Bob, and Alice goes through the flow and does this handshake such that it generates the random number and then sends the commitment to Bob. There's also non-interactive ways to do this. They're a little more complex. So the downside of the interactive process is it requires an additional round trip between the sender and recipient. But you can try to make this process non-interactive, first with a deterministic signature scheme. So something like RSA, an RSA-based signature scheme, or if you have a deterministic ECDSA signature scheme. And what this would allow you to do is if you know that a particular signature algorithm for any unique input X would generate a corresponding unique output, then what you can do is have the sender always generate a random number and send that to the recipient without an initial handshake. And the recipient just generates the signature over that. And as long as the input to the recipient is unpredictable, then the output is going to be unique, and you can use that output as the random number, in addition to the random number generated by the sender. So the reason that it needs to be deterministic is if you have a randomized signature schemes, which a lot of signature schemes are, you have the ability for people to potentially try to grind through additional output values. So if you have multiple valid output values for a particular input value, you might try to grind through multiple computations and see if you can get a better output such that when hashed with the sender's random number is better for you. Another option is this cool construction called verifiable random functions, originally proposed by Macaulay in a paper called Verifiable Random Functions. Generally, the way these things work is that what the recipient can do is, given some input, it can pass it through the verifiable random function, which should produce a pseudo-random output. And in addition to that, it generates a proof that the VRF was executed correctly. And this could be combined with the micropayment protocol by going to the smart contract and providing the winning ticket, but also the proof that the VRF output was constructed correctly. And the contract can check that for you. The cost of this is to be determined because it depends on the type of curve that you're using in addition to the hash function that you're using. I think there are some IETF documents that describe a particular elliptic curve and hash function combination, but it happens that that elliptic curve, there is no pre-compile for it on Ethereum, so it would be kind of expensive to do, but it'd be interesting to see if you could use another elliptic curve and hash function combination that's still feasible on Ethereum with a lower gas cost. And then lastly, we have replay attacks. We need to make sure that the recipient is not able to replay old winning tickets. What you can do here is just have the smart contract record winning tickets for you so that old winning tickets can't be replayed. You also need to make sure that senders can't replay old sender nonce values that it had previously sent because it knows that those would never generate winning tickets. And this can be done via client-side validation. And then we also have senders trying to replay tickets with old recipient RAND values, which is the random number originally generated by the recipient. And similarly, the recipient needs to do client-side validation to make sure that it's not vulnerable to this type of replay attack. So in conclusion, I described some of the topics that I think are interesting about the probabilistic micropayment security model, in addition to some common client security considerations that I think are common to most of these types of protocols. And generally, I think micropayment protocols with lower deployment costs and transaction costs are possible with some amount of engineering work. But it's important to keep in mind that the client must correctly execute all these off-chain message passing protocols. The client must correctly submit transactions in a timely manner within some bounded time window. And then this is all in addition to correct contract implementation, which is a given because the contract implementation needs to reflect the correct protocol rules. And it's important to note that all of the above are necessary for any of the security properties of the protocol to really hold in practice, or else you still might be at risk of losing funds. Yep, that's it. Thanks.
Yeah, so I'm trying to build an analogy for what you just talked about, and if all of the current implementations of state channels or micropayments is like 2CP, is this kind of like UDP?
I guess in a way.
If not, like where does that, like if so, where does that break down? And if not, what would you consider, like what's a good analogy for something like that?
I think that comparison holds in the sense that like for like payment channels or state channels, generally you need to establish this connection that there's some expectation that it's going to live for some amount of time. And then it needs to be torn down if you want to exit that transaction and that relationship. Whilst with this like lottery ticket approach, there's no notion of having to establish a connection ahead of time. What you do is you can just like fire and forget, and you can fire to a lot of people. But it really only works well if you have a high volume use case, because if you have a low volume use case, the probability doesn't work out in your favor.
Thank you.